We are in the 2.5 notes, and we're going to finish this up today. We've been talking about box and whisker plots, so just as a little review, we're going to construct one today, and it's actually easier to do on ALEKS because you just kind of drag this stuff instead of having to hand draw it, but we'll hand draw one here. Just as a review, the box represents where your quartiles are, so quartile 2 is just another word for your median or the middle. And then quartile 1 is the median of the bottom half. And remember, it doesn't always have to be perfectly in the center. It depends on what the numbers are, and that's what it helps us visualize. Quartile 3 is the median of the upper half, and then the whisker parts just connect our min and max entries. So we're gonna construct one. So obviously we have to find all of these specific statistics of our data set. We'll find the minimum, median, quartile 3, all that good stuff, and then basically we'll just draw one. Okay. So here is our data set on the next page here. Below are numbers of hours that a sample of 19 college graduates reported working last week. This is using the tools provided us because I just screenshotted this from ALEKS. Construct a box and whisker plot, also called a box plot, for the data. Since this list is out of order, I do think it's helpful, especially when you're finding the median, to rewrite it in order. Smallest to largest. So I'm going to do that quick. So my lowest is 35. And we do have to find the min and the max as well. So this will be helpful. 35, 36, 41. There's two 42s. 44. 45, 46 and 47. Hopefully I don't run out of room here. 48. Two 50s. What's my next one? 55. It looks like 55, 57, 59. I'll have to move these over. Ooh, not that. Two 65s, 66, and a 69. Okay. If you're ever not sure if you did that correctly, just count them quick. Make sure you still have 19. So I always start by just finding and that's little guideline there. Start by finding your 5 number summary. So your min, quartile 1, quartile 2, quartile 3, max entry. So once you list it, obviously it's easy to identify the minimum value. The lowest value is 35. I'm just going to go in this order because this will help when we're actually drawing the box and whisker plot. And the max is 69. Okay. So next I'd probably find the median. So working my way in, and there's 19 data sets. The one right in the middle here is 48. So I'm just going to kind of do this. You guys know how to find median, 48. What was new for us was finding the upper and lower quartiles. So as a review, lower quartile Q1, that's how we abbreviate that, is just the median of the lower half. So ignore 48 and you just find the median of this one. Just 42. Bless you. And then my quartile 3 is the median of the upper half. So working way in 59. It's my upper quartile. Okay. So then from there, you just draw a horizontal line. So I'm going to use my line tool, but you guys can use a ruler if you want to. I kind of want arrows on both ends, actually. There you go. So basically draw a horizontal line. And then you're going to basically just plot your numbers you found. So I'm not exactly sure if you'll have to decide like what numbers to come up by, but obviously I'm going to start with like 35. I mean, you could start with like 34 if you want to, but we don't need to go any lower than 35, and maybe just mark like every 5. So 36, 37, 38, 39, 40. 1, 2, 3, 4, 5 would be 45. 50, 55, 60, 65, 70, and I don't need to go any higher than 69. Okay, so I usually just start by like plotting these 5 points. So my min at 35 and my max at 69. I'll do my whiskers in blue and my box in green. And then my upper quartile, or my Q1, is 42. Median, 48. Quartile 3 was 59. All right. So just to refresh your memory, for our box and whisker plot, the box is our quartile range, and the whiskers just give us the range from our min to our max. So once you find those, you just create your box around these ones. So I use like a straight edge here. There's your box. And then the whiskers would just connect to these. Like that. Okay, so remember with these quartiles, this is still representing 25% of your data. So is this one. Just because this one's larger just means these ones are more spread out. Okay, and this 25% that's in this quartile is just within like that smaller range. So keep that in mind when you're like interpreting the box and whisker plots. I like those problems where you have to like kind of compare the two. Oh yeah, we did like a cycling one of the 2 athletes is what we did. Okay, that's pretty much it for box and whiskers plots. So just to summarize again, like these ones, like I was saying, where is it? This one. Even though it might look like athlete A ran more miles, it's saying they both ran 60 miles. And what this allows us to see is kind of like the spread of data. Obviously, athlete A just has like a wider range with like the highest mile run they ever did was like 37 and the lowest was 14. So they just have more that are all around the same value. And that's what the box and whiskers like shows you is the spread. All right, next thing we got to talk about are percentiles, which you've probably heard of before. These are like really common in like standardized tests. So if you ever got back like those little like summary of where you scored, or like sometimes it's like below benchmark, above benchmark, or it's like you are within the 52 percentile for math. Okay. So a percentile represents the percentage of scores that are equal or below a certain score with a given sample. It's basically a way of describing kind of like your location. I like to think of it this way: location of a score. And percentiles range from 1 to 99. The first to the 99th percentile. Okay, so I like this example. Oh, I should have found one more thing like the ACT because you guys don't take the SAT. But let's say the 75th percentile SAT score for incoming freshmen into some college is 1,400. So basically, another way to think of like percentiles is they like split up your data into 2 separate groups. So what that means is if the 75th percentile is at that score of 1,500, is that 75% of the students scored that or below, okay? Meaning the other 25% scored higher than that. So if you're like in the 99th percentile, you scored higher than 99% of the other 12th graders in Wisconsin, or whatever it's measuring. Okay. So in this case, you're gonna think of it as it divides it into groups. First group, 75% that scored 1,400 or below. Second group, the 25% scored above 1,400. Okay. So like I said, if you're in like the 99th percentile, like that means you scored like better than 99% of people. So sometimes it can be a little confusing because people like tend to get them mixed up. But I think if you think of dividing it into two separate groups, that kind of makes more sense. And like I said, you've seen this before. So the higher the percentile, you're scoring like higher than that amount is another way to think of it. Oh yeah, let's look at this example. This is just like kind of interpreting percentiles. Another thing with percentiles, they're just really a way of like kind of comparing you against other people. Just because you score in the 99th percentile, that doesn't mean you got 99% of the problems right? That just means like up against the sample of 12th graders, you scored higher than 99% of them. So that sometimes can be confusing too, because we often use percentages as like, oh, you got a 75% on your test. That's different than percentile. All right, so let's look at this example. Government agencies keep data about the income distribution of the population. The Jackson family and Hernandez family live in a county with 11,000 families. The Jackson family's income is at the 82nd percentile. Okay, so that's high. That means their income is higher than 82% of that population. The Hernandez family income is at the 21st percentile, so that's lower. Which of the following must be true about the Jackson's family income? All right, option A. The Jackson family earns more than about 18% of families in their county. Okay, I just basically said that. Because they're in the 82nd percentile, that means that they earn more than 82%. So that one's false, not 18%. About 18% of the families in the county earn more than the Jackson family. What do we think about that? That's true, yeah. So he's at the 82, so think of it like splitting up into two groups. 82nd percentiles here. So their family earns more than 82 or less, meaning that other 18% in that second group earn more than him. That's true. So obviously it's this one, but let's go through and read these other ones. The Jackson family earns about 82% of the highest. Okay, so these two kind of go hand in hand with what I was just saying. The percentile doesn't tell us exactly like the dollar value. Okay, it doesn't mean that they earn 82% of whatever the highest total income is. It just means that they earn 82% more than the people below them. Okay, but it doesn't tell us. Let me write this down. Percentile does not tell us value. In this case, dollar value. Okay. Let's try one more. So which of the following must be true about the Jackson family and the Hernandez family's incomes? Option A, the Jackson family earns more than the Hernandez family. Both the Jackson family and the Hernandez family earn more than the median income. The Jackson family earns $61,000 more than the Hernandez family, or the Jackson family and Hernandez family both have incomes in the bottom half of their incomes in their county. All right, I'm automatically going to rule out this one because, again, the percentile tells us nothing about the actual dollar value. Median income. What percentile do we think would be the median income? What makes sense? 50th, exactly. Median, or Q2, however it's phrased, would be the 50th percentile. Are they both above the 50th percentile? No, that's false. Jackson family is only at 18. both have incomes in the bottom half of income. So I'd be like below the 50th percentile. That's false. So since the Jackson family is in the 82nd percentile, Hernandez is 21st. We do know that they earn more. We don't know how much more, but that's what we can interpret from like the percentile. Okay, sometimes percentiles can be kind of confusing. So now we're going to actually calculate percentiles. These are kind of fun. They're mathy. Okay, so you might be asked a couple different types of questions. So you might be asked, like, what's the percentile of this specific data entry? Like, if I gave you lists here, like, what's the percentile of 34 or something like that? Or they might ask you, like, find the actual, like, 70th percentile. So I'm going to give you two different formulas here. Hopefully they kind of make sense. And once you do a couple examples, you'll be able to decipher between the two. But if you're asked to find the percentile of a specific data entry, so percentile of, I'm going to call it X, which I have kind of bolded up there. You just take the number of data entries that are less than that value. I'll put entries. Divided by the total number of data entries. So basically like finding a percent and then times it by 100. Okay, so that's if you're asked to find like the percentile of some data value in your set. I didn't put an example like that because it's, like I said, it's pretty much just calculating the percent. I did think I put one problem in your homework, so if you need to reference that formula, Alex also has all these formulas on there. If you're asked to find like what number is the 25th percentile, like what's that cutoff, then you're going to use this formula in red that I'm going to do. So this is when you're actually like given the percentage. Well, do I want to say percentage? No. I'll do the TH one. You're given like the 25th or 70th percentile. You're going to take the number of data entries. Alex uses N to represent that. Times P over 100, and P is the percentile. Okay, so we'll try a couple of these because I think these are just like a little bit harder. The following are the PE ratios, price of stock divided by projected earnings per share for 15 banks. These are kind of out of order, which doesn't technically really matter, but it will help us when we go to locate which number is our cutoff number. So I'm going to reorder these quickly. Let's just do it right below here. So 14, 15. So it's not going to matter like in our calculations, but it will help us to identify what our cutoff number is. Okay, 2 18s, or only 1 19, 21, 3 22s, 2 23s, 38, 43, and 50. Okay. So there's our list. And this will help you visualize too, like once you actually calculate the 25th percentile, like does that make sense? Would 25% of my data fall at that number or below it? All right, so 25th. So if you're asked to calculate the percentile, you just take your number of data entries times P over 100. So it says there's 15 banks. So I take 15 times 25, because it's the 25th that we're calculating, divided by 100. Now you're going to get either an integer or you're going to get a decimal. And in this case, I get a decimal, 3.75. So when this happens, you're essentially calculating, you guys, like which number on your list is the 25th percentile. So if I say 3.75, anytime you get a decimal, you're always just going to round up to the nearest integer.
Even if it's like 3.25,
Yep.
round up.
Yep. Yes. Round up to the nearest integer. So this essentially is calculating like the position. So we're going to round up to 4. So that means the 4th number in your list of these 15 is where the 25th percentile is. Because you're essentially kind of like calculating like a 4th of 15, really. That's what this is, a 4th of 15. And since that's a decimal, we just kind of round up. So looking at my list here, 1, 2, 3, 4, 18 is in our 4th position. So to answer their questions, our 25th percentile is 18. Okay, so think about like why this formula makes sense. If I want to figure out the 25th percentile, that's obviously a 4th of 100%, right? So that's what I'm calculating there. A 4th of my 15 data entries would be about 4. So 4 numbers in, 18. That would tell me 25% of the banks have this ratio of 18 or less. Okay, that's what percentile means. If you're like, feels like a pretty complicated question to answer, pretty simple like math. It gets a little bit harder, like if you're doing like 70th percentile. I mean, then you're just doing 7/10, obviously, but this is the formula that they use in ALEKS, and I think it's fine. 70th percentile then, so I'd take my number of data entries, which is 15, and I'm just basically calculating where is 7/10, or 70 over 100, that would give me the next 70th percentile. There I get 10.5, so I'd round up to 11. It's at the 11th spot in your data. All right, 4, 5, 6, 7, 8, 9, 10, 11 is 23. So my 70th percentile is 23. Okay. That's how you calculate percentiles. Figure out of your data entry, where is 70% of that? That's what you're doing here. Round up if needed, and then figure out which data entry that is. One last thing.
Interruption. Sleeping virus, Claire Slister, and Peggy Weber, please report to the conference room.
Okay, one last thing we need to talk about in chapter 2, and this is like a pretty commonly used like statistic, I'd say. It's something called a z-score. So it basically, in short, it's the number of standard deviations a value lies away from the mean. Okay, so if we were to think about this on like a bell-shaped curve, if I were to kind of draw a sketch. Here's my bell-shaped curve. If these down here were z-scores. Okay, remember on a bell-shaped curve, like your mean is right here. This would have a z-score of 0. So you're 0 standard deviations away from the mean. And then obviously like it could be 1, 2, 3 standard deviations away, -1, -2, -3. Here's the weird thing with z-scores is they can be positive or negative. Okay, that's what this is basically saying here. A z-score can be both positive, negative, and it can be 0. When it's negative, that just tells you that your x value is less than the mean. Okay, that your data value is going to be less than the mean. When it's positive, we know it's greater than the mean, and if the z-score is 0, we know that the data value is exactly at whatever the mean is. So to calculate the z-score, pretty simple. You just take the value minus the mean, and you divide by whatever the standard deviation is. So, anytime we get like numbers such as like 3 or -3, we know that's like pretty unusual because this, in a bell-shaped curve, I should say. In a bell-shaped, in a bell-shaped curve, we know like obviously whatever percent of the empirical, whatever percent of our data lie within here. So if our z-score is somewhere between -1 and 1, that's like a pretty usual, like it's nothing weird. That's kind of where they all lie. But as our z-scores get higher, like you get a z-score out here, 3 or -3, we know that's kind of an unusual value. So that's what this is saying. A z-score can be used to identify, hey, how many standard deviations do they lie away from the mean? It's really high or really like negative. That's going to be pretty unusual. The only other thing I want you to maybe put in your notes would be the symbols for this. So if we're talking about a sample, we'd calculate the z-score by doing the value, which I'm going to use x, minus the mean, which is x bar, divided by standard deviation, which is s for sample. And then for a population, the z-score would be x minus, this one's mu, divided by that hat one. I forgot what it's called. What's that symbol called again? Isn't it sigma? It's sigma, but yeah, not the E. Okay, sigma. All right, so just a couple different types calculated the z-score, but it's pretty much as straightforward as that formula. And again, Alex will give you that formula. I'm not a big formula memorizer. A highly anticipated sci-fi movie opened in theaters with a special midnight showing this past Friday. For the Saturday edition of his town's newspaper, Keith wrote a column about local interest in the movie. He found that the attendance for the midnight showing for all the theaters in the state had a mean of 280 people, an average, with a standard deviation of 31 people. So again, standard deviation is on average how far were data from the mean on average. That's what standard deviation is. The attendance for the midnight showing at his town's theater was 255 people. Find the z-score of the attendance at the theater in Keithstown relative to the attendances among all the theaters in the state. Round your answer to 2 decimal places. Okay, so this is a sample. So I'm going to use the symbols as a review. So to calculate the z-score, you just take the data entry minus the mean, divide it by standard deviation. So we want to calculate the z-score relative to the attendances among all the theaters in the states. All right, well, they tell us our mean is 280 people. And they tell us our standard deviation is 31. So we want to calculate that for the attendances at the midnight showing when it was 255. There's my data value. Okay, so obviously in your calculator, 255 minus 280 divided by 31. Keep in mind, we can get negative z-scores, which we do. That just tells us that our data entry lies below the mean, which makes sense because 255 is less than the mean. So rounding this to 2 decimal places would be negative 0.81. That's the z-score. So if this was like a normal distribution, that tells me that that's, relatively usual. It tells you how many standard deviations. If the standard deviation is 31, it doesn't lie a full standard deviation away from the mean. Oop. Which makes sense, right? Because if it did lie a full standard deviation away from the mean, what's 280 minus 31?
249.
249. So it doesn't quite lie one standard deviation away from the mean. It lies negative 0.81. Okay, thanks. That's what you're calculating. Does that make sense? That's a z-score. I don't like doing math in my head. I don't like either when people assume that I'm a math teacher, that I'm a human calculator. If I told you guys that story, they're always like, oh, you're a math teacher. What's the square root of 477? I was like, I'm not a calculator. I'm actually pretty not great at mental math. All right, last one, and we're done. Melissa is in her first semester at a certain university and is taking a calculus course with a large enrollment. She just took the first midterm exam and she's nervous about her score. Among all the students in the course, the mean of the exam was a 57. Ooh, hopefully it's out of 58 points. With a standard deviation of 9. Oh, never mind. Melissa scored an 83 on the exam. We'll just assume they're talking percentages. All right, so find the z-score of Melissa's exam score relative to the exam scores among all the other students. All right, so you don't have to write this formula down again if you don't want to, but we know Melissa scored an 83. That's my data entry. Minus, we know the average or the mean was 57. And we know the standard deviation, on average, people deviated 9 percentages around 57. All right, before I do any math, since she's above the mean, should I get a positive or negative z-value? Positive, yep. So I get this. What do you want me to round to? 2 decimal places. So that's a pretty unusual high score. So she did well. All right, so then part B is just asking you to interpret the z-score. So Melissa's exam score was blank, standard deviations, 2.89, standard deviations, and then this one you get to choose above or below because it's positive, above the average exam score. Okay. Whoop down. Lots of different vocab in that lesson.